Today's talk is about the flow size distribution of sea ice. I just want to highlight this one because the here throughout the talk I'm talking about the flow size only. So which is the size of the ice flows of the Arctic sea ice. But I want to point out this particular parameter has not been routinely observed by the satellite. So previously, we some case study done driving some flow size of flows of the Arctic sea ice, and then analyze that way. But however, throughout this presentation, you will realize this is one of the very important parameters in changing Arctic sea ice because of declining sea ice and expanding of the marginal ice zone. So today's research is from many different collaborators, but I would like to acknowledge Yan and Hwang, the PhD student. So most of the model and observation comparison research is from her work. Yeah. So this is a brief outline of the talk, and first I will discuss about the expanding marginal ice zone and talk about what's the marginal ice zone and why is it so important for the Arctic sea ice. And then I'll show some of the examples of the satellite observation of flow size. And then finally, the model and observation comparison studies. So I think already in a previous presentation, talk about the declining of sea ice in the Arctic. It's very obvious. But I want to point out one very important aspect of the declining sea ice is the major consequence of Arctic reduction of Arctic sea ice is the expansion of so-called marginal ice zone. So here in next slide, there's a three key point describing what is marginal ice zone. Also, you can see this video here. So what it look like in like a visual sense here. And the first thing is the marginal ice zone is commonly defined wherever the ocean area with ice covered ocean, the waves and swells affecting the ice. As you can see here, the waves coming in affecting the ice. And second definition is such a dynamic area where there are low ice concentration, like 15% to 80%. And also that area is characterized by the very distinctive ice pieces, as you see in these satellite images. And from analyzing the satellite image, define the marginal ice zone width between like 15% to 80%. They analyze how this MIZ width has changed over time. And in here, you can see the summer marginal ice zone width from July to September. You can see quite a significant increase of the width. And also in these SAR images, satellite images, you can see 2005, you can see this white area is ice and black area ocean. You can see largely part of the ice is ice covered. However, in 2016, you can see pockets of the very fragmented sea ice, white speckles. And also you can see large areas open water. And then looking forward, the projection of how this marginal ice zone will expand is very significant as the ice decline. So that's one of the motivation of the recent modeling and observational study actually very emphasize on this so-called marginal ice zone process. And then they're trying to incorporate that process into new sea ice model, and then so that they can produce the better prediction for the Arctic sea ice. And now I'm going to move to the previous observation done and in terms of as a part of the US ONR MIZ program. So in this program, happened in 2014, we deploy the many different autonomous buoys in the Arctic, and then we have 4 different clusters of these buoys, and then we monitor how we drift, and we measuring all different types of the parameters. And in this animation, it shows you can see these points are popping up. These are the buoy clusters. And then you see these are the drifting over time from April to the August time. And this blue area is the open water area. So you can see how this cluster of buoys drifting alongside of this changing Arctic sea ice concentration in the way. So for my research on this part was what was the major cause of the floe breakup, and then was it the wave or swells breaking up the ice floe as we traditionally kind of believed, or something else? And to do that, we acquire the Terasa XR images along this buoy track, these yellow lines, and for different buoy clusters. So that series of these SAR images can provide a temporal evolution of what's happening in the sea ice in terms of flow size and also the ice concentration along the way. And so, as I said, the seasonal evolution is a part of the life cycle of the sea ice. So in the winter time, you have like a continuous the ice cover, and then as spring comes, it starts to melt from the surface and the bottom, but they start forming the melt pond. You can see here, and then in early summertime, it starts to break into a very distinctive or discrete the piece of the ice we call floe, and this floe start to break up further into smaller floe, and then or melt. And then eventually it goes into the open water conditions. So there are a number of the ways of breaking up the ice floes, and most important thing is the wave or swell induced breakup here. So it can break up in half of the ice floes, and then also it collide each other between flows, and then it impacting the flow size in the way. And also they can develop the cracks within the ice floe, and then they break up. It can be either like through the deformation event or other event. It can break up through the cracks developing. And also the thermodynamic aspect is the lateral melting, which means the boundary of the ice floe touching the warmer ocean. So it not only melting from the bottom, also melting from the side. So actually it affecting the flow, general ice concentration, and it kicking up the positive feedback on the reducing the sea ice concentration in the way. And also this lateral melting is most significant in smaller ice floes. So that's why the modeling people are very curious about the small ice floe than larger ice floes. So that's another point I'm trying to make in the next slide, and then why we have to go with the smaller, the high resolution images. Yeah. Okay. For now, for the ONR MIZ project, we use the Terasa XR images, and then you can see the evolution of the ice conditions from 15th of July to August, and these are the low images, and then these bottom ones are the one we extract the boundary of the ice floes using the algorithm. So once we get this extract the boundary of all these individual ice floes, then we can put those data into the graph like this one. So we measure the flow size of flow in terms of the mean caliper diameters in meters, for example, and then we create a cumulative flow number density And then you can, and then this distribution, flow size distribution, and then we can assume as the power distribution. So in this power distribution, this alpha value, the exponent, actually giving us a very good information on the status of a flow size. For example, if alpha value is smaller, 1.5, for example, then we can expect to see a larger ice flow among a few small ice flows. However, its alpha value, the exponent is higher. That means it indicates the very many small ice flows with some intermediate size of the ice flows there. So then you can actually display the exponent alpha value over time from the satellite images. Then you can see this seasonal evolution of the alpha value and also the number of flows. And you can see generally the alpha value increase, which is indicating transition to the smaller flows in the of Arctic sea ice. But one thing what we kind of surprised to see was there are certain period in mid-August, we see a very sudden jump in the alpha value, which is an exponent across all these clusters. And also it sees from the number of flows. And then we start to question why what is causing this certain increase of the alpha value, which indicating a sudden fragmentation of the Arctic sea ice. So first we turn into the wave and swells because they are the major mechanism to break up the ice flows. And also before I go there, and then this one also shows the more detailed view of how this mid-August flow fragmentation happened. So you can see from July to end of July, you can see the number of ways you can see. You can see from the figures here. Also you can see from the number density how the smaller flows suddenly increase for the 12th of the August. Or you can see from the cumulative distribution, you can see 12th of August, you see the big increase of alpha value compared to the other dates, like end of November or mid-November. So that indicating there was certain change in this flow size happened between the end of July to the mid-August time. So as I said before, we first thought this is about wave, because wave came for that period and break up all the ice flows. However, as I said, in MIG program, we had the wave buoys installed on the cluster, so we can measure the wave on that spot. And what turns out is these are red vertical lines are the 12th of August. And for that time, these are the indicating the significant the actions from the waves. So only that the wave with the clusters, buoys, the ice will felt waves and swells after the 12th of August. So before actually that we see the mid-August fragmentation, we didn't see any wave felt by the buoy clusters. So that was interesting because we thought it's a wave and it's not a wave. So and then another reason it's not the wave is we kind of measure the distance from the each clusters to the ice edge. And it turns out even 12th of August time, the distance from the clusters to the ice edge were like more than about 100 meters away. So that's also confirming it may not be the wave actually causing the change. And then we look at the thermodynamic melt of the Arctic sea ice from a vertical melt. And then because we have an ice mass balance buoy on the side, so we can measure how much total ice melt happened for the period. So it happened about 1 meter, the ice was melt vertically. So that indicates some of the thin ice amongst the thick ice maybe just melt out. And then, so we just think the thermodynamic vertical melt has a very significant impact on this mid-August flow fragmentation. And then we look at some of the satellite images of SAR images, and we look at the particular two pieces of ice in this in winter time. So this white ice indicating like a thick ice, and this black ice indicating thin ice. So you can see these orangey kind of flows are intact for the in August 8th. However, these yellow flows are gone, breaking up. So we kind of thought this is due to this melting of this thinner ice, and they can kind of indicating the significant impact on thermodynamic melt on this. And then we moving on to the how the observation can help the sea ice model. So we incorporate the sea ice flow size from the satellite to the sea ice model, and then with Zhang, and then so he found out there are some difference can make incorporating the flow size parameterization into sea ice model. And now is more modelers are developing and incorporating this sea ice flow process into the sea ice model. And there are two different framework going on. One is a power law model, and the other one is a prognostic model. But I don't want to go detail. But the power law model is basically taking the information from the observation and assuming the power law, and you use that one to simulate the flow size in the model. The prognostic model is completely different. They start from the beginning purely based on the physical process and simulate the flow size. And so it's very critical to we evaluate these models. And one thing came out when we discussed with the sea ice model is they won't have resolved the smaller ice flows, not the larger ones. So that's why we start looking at the 1 meter resolution satellite images. And also, we're going to try to look at what going to be the impact of the even higher resolution to the flow size distributions. And this let me summarize on some of the aspect on that one. Between the 1 meter resolution and half meter resolution, generally the flow size division shows a similar trend until about 20 meters in size, and then they make quite a difference between these different resolution. So that's one of the way we keep pushing our limit to having a higher resolution to actually we can correctly resolve the smaller flows for the modeling comparison. However, the half meter resolution data is not widely available in the Arctic. So, but we have a certain quite a data set from media data from NASA initiative. We have 3 different sites. We analyzed these 1 meter satellite images, and then these are one of the examples showing the regional difference, showing the Church's Sea site actually showing a higher flow perimeter density, which means they are indicating smaller flows in the Church's Sea side than Fram Strait in this site. So it kind of this data set, we look at it and make sense, and then because of the different sea ice regimes. And then what actually we look at more details on that, and then it shows one of the interesting aspect was the Church's Sea site, which is in this area here, actually shows some trend on seasonal evolution from the larger flows to the smaller flows. We had the data for 2013, 2014 analyzed. However, what was interesting in a Fram Strait site, and we don't see any big seasonal kind of trend in the flow size distribution. That was interesting to see that one. So this analysis is ongoing. On the final slide, I want to highlight on this. And it's the first time we try to kind of compare the flow size in terms of perimeter density per unit ice area between the observation and model. We choose the 3 different model. CPAM in UK, they have a prognostic model and 2 different types. And also this WPO FSD model is the power model. So first thing and then this black dot and black lines are indicating the observation data. So what is actually this one indicating is the observation actually shows the perimeter density of the ice flow increase with a smaller ice concentration. I think which makes sense because the if in a smaller ice concentration, we might expect to see more smaller ice flows. So it makes sense. And then at the same time, these red dot and red lines are indicating the result from the power model, which is similar to the observation. And also this makes sense because the power model adopt the power from the observation. However, a little bit surprised to see the prognostic model show the opposite trend and to very different values. And this is currently under investigation. And then the major point of this showing this result is we are trying to validate this CIS new type of CIS model, including marginal ice zone with observation, and this will continue and then to validate and calibrate the CIS model there. So very short conclusion is I want to highlight this CIS flow size is very important CIS parameters to be observed and modeled. And it's even more important in the changing Arctic Ocean, like reducing sea ice. And also the recent observation shows especially in Churchill Sea, how the ice is breaking up is changing our understanding, because previously we thought is a wave and swells, but now we think thermodynamics are more important in that area. And also the significant development CIS model, and to incorporate this important process, but the performance of this parameterization is still remain to see at this stage. Okay, it's the end of my presentation, and thank you. If you have any question, please do contact me in email.